This is the Amp Hour Podcast, released January 26th, 2020. Episode 476. An interview with Kendall Castor-Perry. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
Hi, and I'm Kendall Castor-Perry. They call me the Filter Wizard, though I didn't invent that name.
Wow, I feel like if you did, though, we could have like some kind of like magical sound effect here or something like that. I don't know.
Well,
we might put that in.
Feel free to add that, yes. I mean, my daughter's a massive Harry Potter fan, so,
Okay, there we go.
I'm sure
right.
when she was younger, she would have imagined me being in a kind of flowing robe with kind of arcane symbols over it. Of course, they wouldn't have been arcane at all. They would have just been transistors and op-amps and things.
Right.
But what would she know?
But to the layperson, then, arcane,
Yeah.
And so actually that's a great lead in here. I mean, filtering in general is kind of this it is sort of black art, but it's analog in general, and it's confusing for a lot of people. So what is the genesis of being called the Filter Wizard, and what did you like working on that got you there?
Oh, blimey, that's quite a difficult one. I mean, I've been doing filters my whole professional career. So, I mean, just as a kind of potted bio, when I was in the kind of that little gap period between the end of school, high school, just senior school in the UK, and going to university, I'd already got my place at university. I was looking for a job. And because I've always been interested in audio and hi-fi, I looked around the various hi-fi companies in my area and decided I was going to go and basically visit one of them, just basically rap on the door and say, give me a job. I'm interested in hi-fi and I know a lot of stuff already. So I had to walk some distance to a particular bus stop to get a bus that went to the place where this hi-fi company was. And I walked past this storefront in a kind of parade of shops, and, nothing, you couldn't see much through the window, but there was a sign in the door saying wiremen wanted. Of course, I knew what a wire was, but I had no idea what a wireman wanted. And so I was obviously intrigued, did a chin scratchy thing and went, well, I'm going to go in because if it involves wires. So I went in and asked the secretary, I said, do you have any jobs for an aspiring young electronic engineer? And she kind of was a bit baffled, really. She said, well, I don't know, but I'll get Bill to ring you back. Give me your phone number. So I did. And then I went on, and I think I never actually even got to the hi-fi company. It's Rogers, the loudspeaker company, which was excellent in those days. And then Bill Meek, the guy, one of the founders of this company, Chemo, that I ended up working for, he rang me back and said, what tell me about yourself. And I said, I've been interested in electronics since kind of I could barely walk and that sort of stuff. And he said, oh, that sounds interesting. Come in and have an interview. And so I went in the next day to talk to them, and it was the lunch hour. And there were all these guys, they're kind of in, denim, long hair, and they were basically kind of checking out their home build stuff like amplifiers and electronic speedometers and stuff like that using their company's equipment. I thought, wow, fantastic. This is the place for me. These, and the people there who run it said they explained that. They said basically, we give our people can do anything they want and, use any of the components they want, as long as it's not crazy expensive or something that one of our customers actually gave to us basically because, we want them to be interested in this kind of stuff. I thought, fantastic.
So basically
I'm going to start working there.
Catnip to a nerd, right? Yeah.
Absolutely. It was sprinkled down. This electronic catnip was sprinkled down from above. And the long and the short of it is I stayed there for 21 years.
Wow.
So basically my first job was sweeping the floors, and I ended up being the managing director. So
did you ever find out what a wireman was?
Yes, it's a person who does wiring.
No, there we go.
There we go.
All right, true to form.
Yes, it's not a terrible insight, but no, and that was one of the main things that the company did was filters, because it was the start of the kind of, I suppose, the kind of op-amp transistor era for filters and communications and things like that. And both of them had expertise, the guys who founded it, in filter design and kind of designing various kinds of industrial and scientific instrumentation. They decided to start out on their own. And so a lot of the things the company made were filters, and some of them were active filters using op-amps, fairly early op amps, kind of weird things you don't see that much. Some of them were passive filters, so we had old Ted, the guy who used to work for the British Post Office until he retired, with a fabulous winding machine. I'd call it Heath Robinson. I think you in America call it Rube Goldberg. A kind of weird thing. It's like if you took a sewing machine and then rebuilt it inside out. That was kind of what it was. And
Nice.
he had, shelves of wires, and he did that. And he also selected the capacitors. He had an ancient capacitor measurement thing, the kind of thing that Michael Faraday probably would have used. And basically, because the company used to build things where you needed pretty precise inductors and pretty precisely known capacitors, he would get these boxes of capacitors and he'd measure their value and he'd write the value on the side in red Sharpie. So basically, every capacitor in the place had gone through TED and it had its value written on it. So I learned a lot about passive filtering and stuff like that. But basically, it was just a long, slow process. We had a fantastic library. We used to get regular, in the days well before the internet, we used to have a library service from the British Library. Basically, every week would come this thick sheaf of paper extracts. And basically, I could just get any of them I wanted. So I just accumulated, it must be into the thousands of papers on filters. They had great books. And they said, if you ever see a book you like, buy it.
Man. That is the dream. That is the dream.
It is, and at the same time, I was using great components from, people like National, TI, in the days when their data books and application handbooks were the gold standard for, knowing anything. And I basically I lapped them up, really. I just cover to cover. They were my touchstones. And, I'm in California now, but I remember in those days, even, you'd see the names of where these companies were, and it would be places like Sunnyvale and Palo Alto. And in my mind, there was this kind of heaven of analog electronics, where the sky is always blue, the sun always shines, the place names are fabulous, and there are super smart people who design op amps and then write books where they tell you how to use them. And I thought, that's just one day I'm going to go out there. I'm going to get out to California somehow.
Wow. And and you did.
I did, eventually.
I'd love to hear about the interim, but I'd actually like to hear a little bit. Let's dive into the actual mechanism of filtering as well. I mean, so you mentioned passive filters, you mentioned active filters, and you mentioned obviously op amps and active components are part of active filtering. But what is kind of your go-to? I mean, if someone comes up to you these days and says, "How do I start learning about filters?" Where do you usually point them?
Wow, that's really difficult. I mean, in terms of books, I have some favorite books, but they're all relatively dense. In terms of simple books, I know a lot of people talk about Don Lancaster's Active Filter Cookbook, and that is a great book. But that's really, it kind of sidesteps the understanding what's going on and just basically gives you a lot of clues about how you would make something if what you really want is just to make something.
Right. And if it goes wrong, then it's kind of you're on your own then, right?
Yeah. In terms of understanding, I talk to a lot of people, and it's very common these days that people kind of want to get that shortcut. They want to go, just traveling without moving thing. They want to get to know how to do something without really putting the calories in. And I think, you do need to have, a certain amount of math and a certain amount of physics. You need to not be frightened of complex numbers for a start. A little bit of calculus doesn't hurt. Basic circuit theories is if you have the opportunity to learn that, that's quite a good idea. And I'm sure now, with so many of the great educational establishments putting their material online, there are probably some great circuit theory courses that you can kind of sit through, and it does help. I am a bit of a stickler for that. There was a time when I was young when it was basically ready, fire, aim, and I was, I would just kind of, and I'm still in a way a bit of an experimenter. I do believe in allowing a bit of creativity, but eventually you find out that you have to understand the reasons why something does the thing it does. Right. Otherwise, you can't, because if you don't understand where you are, you've got not much choice of understanding the shape of the surface of the space or whatever that you're in. So you don't know where if you make a move, you don't know what's going to happen. And that it always scared me a little bit. So anyway, back to the question. I think you could always start with a resistor and a capacitor, basically. Low pass filtering and high pass filtering. It's a standard interview question. I guess you're going to get that when you go for a interview for a job where there is some analog thing. You need to have an intuition of if someone gives you a resistor and a capacitor, and then you put a signal into it, with a voltage signal or maybe a current signal, basically, what do the wave shapes look like?
Right.
So in order to even really grok the idea of what a wave shape looks like, it really does help if you've got learned to how to use a scope. I think the scope has to be the most important piece of equipment. Probably, if you're talking about the 31 signs of a real electronics guide, basically one of them has to be, you need to know your way around a scope, and you need to understand what it is that it's showing you. So you need to be able to put in a waveform from a waveform generator and go, oh, I understand that. And then you need to put it through a circuit, and the shape of it changes on the screen. And you go, I can understand what I'm seeing there, and I can draw a graph, or I can do a sum and go, yep, I know why that's happening. I think it's about building that kind of a core understanding, because it's like architecture really, and building foundations of things. Basically, if you haven't got good foundations, the thing you build on top of it will eventually fall over.
Right. Yeah, it is that intuition. It's intuition, effectively. And then, like you're saying, I mean, you don't have to dive right into the math, but at least understanding that, like, oh, okay, well, the corners are going away on that square wave, and now why is that? It's like, oh, maybe I should look at some Fourier stuff. You probably wouldn't think that, but eventually you'll get there, and then you look at the math, and you'll look at the this and that.
So if you come to it from a physics point of view, and you just look at what a capacitor does, and then you can work out that there's some exponential thing going on there, basically, and without even really thinking about sine waves and S domain or Z domain or whatever. It's just in the time domain, the physics takes you there. I mean, I'm a physicist by training, really, so I guess that kind of thing, the ability to represent something with a bunch of equations to kind of actually be able to relate some independent variable to some dependent variable, comes naturally to me, and it's quite helpful to be like that. I think if you come to it without if you skimmed over physics at school because you kind of thought it was too difficult, or you didn't like the teacher or something like that, it's kind of a bit more difficult to reverse back into that space, because you haven't got a mirror to look to see what you're going to hit.
Yeah. Well, so you had said you were working at this company right out of high school. I mean, at that point, did you have kind of the math knowledge or the physics knowledge, or was that like you were kind of working your way into that as you were going into college, and then you also had this interest on the side?
Incrementally, yes. Yes, I did. I mean, I started out with electronics fairly early on. I mean, my parents owned, slightly against their will, a very big house. And, in order to make ends meet, they rented out rooms in it. So, I grew up in a house where there were always a lot of tenants, who would stay for a few months or a few years or whatever. And, they were usually quite young people, and quite young people in those days had record players because they would like to listen to their young people music. And their record players would often break. And I'd go, let me have a go at fixing that, with variable success, I have to admit. But I learned, I was interested in music and what went on in those, and in the old televisions that we had lying around the place as well. My dad was an engineer, and he was quite interested in electronics. So he kind of learned his way into it. So the house was full of electronics magazines. So right from when I was like 9 or 10 or whatever, I would read these electronics magazines, and there wasn't an awful lot of theory in there. And that was really mostly transistors and resistors and stuff, building things. So building things was the way I started. But because I was quite inquisitive, I wanted to find out how it worked, and I'd always been interested in science. It's the way that, I don't know if my parents steered me that way, or my books when I was young were kind of like chemistry books and physics books, and the kind of monthly magazines you would get would be things like Knowledge and that sort of stuff. And I would fall asleep. I used to have these kind of reinforced glasses because I've been wearing spectacles since I was about 3 for various reasons. And so I would always fall asleep reading some kind of magazine or chemistry book or something, even when I was quite young, and always break my glasses. So that made my parents upset. But anyway, I was interested in science from a very early age. And when I made my choices at school, at the kind of middle school and upper school, it was the same school for me, but we had kind of the various different chunks of school. I always leaned towards science as soon as I could. So, and it's a shame really, because I was also very interested in chemistry. I did at one point make the kind of transition from chemistry, because my first lab wasn't an electronics lab; it was a chemistry lab. I had a pretty amazing kind of chemistry set with all sorts of kind of things. Some of them really rather too poisonous for 10 or 11-year-old
they don't do that anymore.
They really don't. They don't allow that anymore. I think
I remember taking those. Yeah,
I selected the stuff that I thought was the kind of the most dangerous. Phenol, the potassium oxalate, potassium cyanide, that kind of stuff, and took it to the local pharmacists and said, "Can you dispose of this, really? Because I don't want it anymore." And they just roll their eyes and go, "Oh, another chemistry geek." These days, I think you probably get arrested. But anyway, I made the transition from chemistry to electronics, and it's one of the sadnesses in my life because I had a lovely chemistry teacher, Mr. Mallinson, a kind of a really short guy, really, just about to retire, and I was one of his kind of star pupils because I was really quite keen and enthusiastic and kind of got the basics of chemistry, and I gave up I gave it up in order to concentrate on the maths and the physics. So I kind of went into the maths sixth form at school rather than the sort of general science sixth form. And, I think he was quite upset, really. But anyway, I decided that, physics was the way to go because it was, at the time, more of a way, the physics and the maths was more of a way into understanding how stuff worked and, was already quite interested in, transistors. I remember in our, we did English right up to the end because it was, you could have a little bit of liberal arts stuff in there. And so English often, one of the tasks was that everyone had to prepare a little lecture to give to people. So we had experience of basically explaining a subject we really understood or really had an appreciation for to your classmates. And I did it on a common emitter transistor amplifier. I guess this was when I was probably about 15 or something like that.
How did that go over with the class? I imagine there was some
actually
befuddlement.
I had some really tolerant friends, and they were all doing maths and physics as well, basically. So they were.
Oh, okay, that helps.
It was a smart cohort, basically. I was really lucky, and I'm still friends with quite a few of them, and we met for the New Year not that long ago. We're all quite old now, but we still keep in touch. So yeah, I think they were tolerant. The English teacher kind of asked some kind of very kind of tangential questions about it because he wasn't quite so keen. But anyway, another thing I did was a friend of mine in another class was quite keen on synthesizers, and I I was into kind of Emerson, Lake and Palmer and all these kind of things where, sort of aggressively played synthesizers with great kind of sounds were the thing. And so he said, can you make me a synthesizer? You're interested in that. And so I made him a synthesizer. So I learned quite a lot of stuff. And the whole genesis, I suppose, of the filter was my enthusiasm for filters. And this was before I went to work in a company that made them, was the Bob Moog's ladder filter, the voltage controlled filter that he designed for his synthesizers, because the simple way of making those kind of sharp, very characteristic sounds, you take a very harmonic rich waveform and then you put them through a voltage controlled filter with a waveform that's kind of programming its cutoff frequency or its resonance or something like that during the duration of the note, made a sound which was unique and I felt very captivating. And so that was the thing. I wanted to really make a synthesizer because I wanted to play with a voltage control filter. And I think that my love of filtered sounds was what led me to sort of never quite be able to get filters out of my mind. And so going to work for a company that made filters, it was kind of like Kismet or Bichette or whatever some people call it, that it was kind of meant to be.
Yeah, I mean, it sounds like your feet kind of took you there,
yes,
right?
Exactly. Yeah.
And so at Chemo, like, what were people doing with the filters? And so those were going to like studios, or they're going into commercial devices, or
not a lot of
just audio setups?
Not a lot of audio work. I mean, all the audio work was just with the stuff that people were making in their spare time. The filters, I mean, over the period of time, the stuff that I designed went into a lot of areas. But when I joined, they made some general purpose lab instruments. I mean, we always used to say that the first two things you need in a lab, three things, are a scope, a signal generator, and a multimeter. But the fourth thing you need is a variable filter, basically, because if you've got a signal and you need to basically chop out or process stuff to get rid of noise or get rid of a low frequency thing, you need to have a bench programmable thing with a lot of knobs on the front that you can just adjust the frequency. So, and there were various companies
so like a decade
making
box,
that.
but kind of
Exactly
for
that.
filtering.
Exactly
right?
that. And they look very similar to decade boxes, the big knobs on the front. And a company was already making stuff like that. Ones with continuously variable wire wound pots, ones with switches. And when you looked inside, these switches were multi-bank switches with resistors kind of soldered onto them, very, very intensively manually made things. So there was that, and there were also kind of modular filters that would go into scientific instrumentation and some like commercial communication stuff where the requirement for filters seemed to move ahead faster than engineers were being taught how to do it. So I guess the company was on the leading edge of finding that there was a market for that kind of stuff. Because someone would come along and they'd say they'd realize they needed a kind of phase equalized ninth order elliptic filter. How the hell do you do that? So basically, and we were the answer to that question. Basically, when you buy it from us, basically we make it for you. We put it in a little pot, and we kind of cover it with goop so you can't tell what we've done, and we sell it to you for a sort of super high margin price.
Yeah, that's great.
So there was a lot of that, and over time, in the era before the widespread use of delta sigma ADCs, for instance, which tend basically not to have an awful lot of analog filtering, is the data acquisition systems that people use for measuring strain and stuff and processing the data that they would acquire from some test, like some testing a rocket engine or something like that, would all be done with a sampling A to D converter. So it needed to have a front end, with some gain and transducer interfacing, and then anti-aliasing filtering. So in the days when you had to put anti-aliasing filtering in front of a density converter to get good results, there was a substantial market for that. And I suppose a significant number of the things that we did over the course of the time that I was there were for that purpose, for in some way or other, and this was sometimes in the thousands or tens of thousands of channels. This wasn't it ceased to become a kind of, we've got this, there's a lab down the road and they want 5. It's kind of, okay, Siemens are building a body scanner and they want 15,000.
Oh wow! Okay, so like those kind of volumes too.
Yeah. So
is this company still around?
It is. It exists. The guy who's running it is the guy I actually appointed as a marketing director back in 1997. I think.
Oh wow! Okay.
During when I was at the tail end of my time there, and there's still a market for it. In fact, we talk occasionally. Sometimes when he's doing a redesign of a board, he'll want me to help him out a little bit. And I'm quite encouraged by the fact that one of the projects that is still quite successful for him, and he still sells quite a few systems a year, is something I started designing in 1988 and went into first production in 1990. So that's pretty good. I mean, he's done some changes to it with if not sometimes my help, then certainly with my help afterwards, if you see what I mean. It was a great product then, and it's still a great product. So I'm quite pleased that the stuff that I was doing back then, when I suppose was in the kind of peak of that kind of work, is still, there are still people who want it.
That's an interesting point you brought up too about the switch to Sigma Delta ADCs and how that ended up impacting things. I mean, do you see that broadly, or was that something that was very specific to this scenario?
Obviously, you can't avoid it in audio, and I can't think of anyone using sampling ADCs in any realistic kind of audio application anymore. And sampling DACs, if you like to look at it that way, continuous time DACs, are really relegated to the super high end, a particular strand of audiophile super high end. And I mean, I'm quite plugged into that kind of thing because, back in the day, around the turn of the millennium, I was the audio kind of digital audio specialist and audio products manager for Burr Brown at the time. I mean, that's I after my kind of 20-year career actually kind of designing stuff, proper equipment, I made the transition into the chip business where I've been for the last 20 years. And some of the most celebrated D2A converters still use the kind of R2R, the 24-bit PCM 1704, kind of a collaborative Burr Brown Japan and Burr Brown design, very old school, very expensive, very old technology, but there are still people out there who love it. But that's the exception that proves the rule. I mean, these things probably run $20 or $30 a pop now.
Oh wow.
which is kind of out of the range of most systems. But
Right.
broadly
They're
speaking,
like high-end systems, but maybe not
super
consumer
high-end.
level device
Yeah.
like a Alexa or an Amazon Echo might not have it in it, but something else would.
Some sampling ADCs still have their place in a lot of things, but more and more in audio, in interfacing to sensors. The understanding of how to get good performance out of a delta sigma converter is so refined these days that it's the preeminent choice. And of course, they do have filtering in them, but that filtering is kind of there for a different reason. So there's usually very little in the way of filtering at the front end. Usually the only residual reason you need to filter at the front end of a delta sigma converter is if you're interested in the very lowest noise, and you've got a very, very wide band front end which produces noise at such a high frequency that even the super fast sampling of the Delsig could fold it back into the baseband, then you will kind of slice it off with a little bit of RC filtering. But it's not ultra brick wall kind of super sharp filtering like it was in the old days.
So where do you see then? I mean, obviously, we can keep moving through your career, and it's you've been at chip companies like you said for 20 years now. But where then? So someone thinks filtering in 2020. What are a lot of the applications that you see that are out there? Like what are people using active high cutoff kind of filters for these days?
Well, I mean, I'll kind of just break that up into several pieces. First of all, you think where I'm going with this. You might want to chop out as a little bit of sort of chin scratchy stuff. I was going to make 3 separate points.
Well, we can just filter it. Like this is
cool.
It's like editing. Right. Editing is like word filtering
or noise gating or whatever. For a start, an awful lot of the electronics that you find has got filtering in it, but it's not filtering that the customer wants. It's filtering that is inherent to the functionality that the customer is buying. So, for instance, when you buy an audio A to D or D to A converter, there's usually quite a lot of filtering in there, but that's not what the customer didn't buy it because there was a filter there. The filter's all built in, and so if it does its job, you kind of don't even need to know it's there. And that's really people, in the transition from analog filtering to digital filtering, people often say, well, what's better, analog filtering or digital filtering? And kind of basically, then when you make a product like at one stage we did at Cypress, which had a digital filtering engine in, they would say, well, how do we sell this digital filter? Can you sell it instead of an analog filter? And the broad answer to that is no, because the digital filter in a product like that serves a different role. It serves a role of enabling you to complete a function that the customer wants. But the function that the customer wants doesn't objectively contain the filtering. So it's like, for instance, if you want to make an A to D converter with a certain bandwidth, you need the filtering, but the customer expects that to be done. They don't want to have to fiddle around with the filtering themselves. So broadly speaking, the filtering has gone inside chips in such a way that customers don't need to know it's there anymore. They don't need to build them. So the requirement on people who aren't chip designers or kind of really sleeves rolled up system designers is a lot less than it used to. If you look at a circuit board, it's very rare that you'll actually find something on it which is a digital filter that just takes a digital signal that exists on the board and outputs another digital signal that it exists on the board because that's what you wanted to do. Typically speaking, some other guy already built that into the product or wrote some code or downloaded a library from ARM or something like that. And
put an FPGA or something.
It magically happens and you don't have to think about it. And the other point I was going to make is that, and I kind of have said it in the various little kind of bylines and bios that I put there, is that my job, I think, at the end of the day, has always been to chase signals around, because when you build a thing like this, your first step is really to transduce some activity in the real world into an electrical signal somehow, and that's basically what all sensors do. People say something, what's the difference between a sensor and a transducer? And really, a transducer is the little piece of kind of instantiated physics that turns something like a strain or a temperature or a kind of flux of particles or something like that into a signal that you can actually plug into something. So that's the first stage. So sensors contain transducers, but they often contain other stuff as well, like linearization or computation or whatever, and interfacing circuits. circuits. But really, it's the signal that's important. So audio is a really good example of that, basically. So if you think about all the different ways in which the me talking to you is represented to you, I mean, it's made by my mouth. It goes across the air to this lovely microphone that we're talking, goes down. It's a USB microphone, so it has to get crunched by the laptop. So then internally, there's going to be some compression because they don't send it uncompressed over the internet. And it gets, it's being mashed around, but it hasn't lost the fact that I'm going, Peter Piper, peck to pick of whatever. So the thing that's important is the signal. And that's true really not just for voice, but for almost anything. And so I've always said, my job is to chase signals and, they can't hide just by going from analog to digital to 1 bit to compressed to wherever, basically. And I think in one of my bylines, I said, think of me as the Van Helsing of electronic design. Basically, I'm chasing the vampire of the Nosferatu of information, and it can change into a pile of rats or bats or whatever, but it isn't going to escape me because that's what's important. And I mean, I know that's a bit colourful as a statement, but you have to then when you start thinking, well, what are the ways that you represent a signal, and basically filtering in the way of kind of selecting the difference between what you do want and what you don't want appears in different guises in different systems. And I've had over the years to become familiar with the ways in which you apply that kind of differentiation and decision making, not just in the analog domain, but in the sample domain, in the digital domain, and even in the physical domain as well, thinking about microphones and loudspeakers. So there's all sorts of different domains where the signal exists, and you have to do something to it that you could call filtering. It's not just op amps and transistors or DSPs.
I mean, it sounded like you were kind of on the border of like information theory type of stuff too there, like what you're talking about these, this information. Well, you were saying signal, but I was thinking information because it's, at the end of the day, you were saying Peter Piper picks, and it had to get to my ear or our listeners' ears. And that ultimately was the thing that needed to be transferred.
That's the thing, basically. It's not... and a guy whose stuff I read on the on LinkedIn made a good point about his systems. They said that, the hardware is the bottle, but the kind of information or the software is the wine. And, so it's interesting studying the hardware, but hardware is always just a particular instantiation of something that does something to a signal which is meaningful to you. And so there is an information thing. I mean, I don't spend much of my time thinking about kind of Shannon and his equations and what's the maximum information I can get through, because that's not typically relevant to really almost any of the things we do. I mean, I know that there are people doing who will kind of squirm listening to that, trying to get the maximum information throughput through a given channel. And one of the things that's so fascinating about the modern high-speed interfaces between things is just how analog they've become without people thinking about it. You think about, DRAM, for instance, RAM memory, it's as digital as it gets, right? Except once it gets out of the package, you have to send it somewhere else. And you really need to know a lot about the kind of dynamics of copper traces on FR4 and that kind of thing to understand that. And what's fascinating to me is that it's a return almost to filter theory, because what's important is the frequency response, the time response, how that works. And if you want to correct for it, to equalize for it, all of a sudden you're working almost with filter theory to try and fix up this connection between two entirely digital chips. So the information contained on there is it's essentially unknown to you, or should be if it's appropriately encrypted. Basically, it's just a bunch of ones and zeros, or in the sort of slightly more sophisticated case, a small number of symbols, 4, 16, maybe 64. Mm-hmm. But that's going across an analog channel, and you need to understand the analog situation. And that's where a lot of the analog interest is at the moment. I mean, if you're looking for a job in the analog world, the thing that most people are looking for at the moment is what they call SERDES, or the serializer deserializer, because people realize that the most coherent way of getting lots of data across was using a smaller number of lines as possible. So you go very fast, but you have to understand how this data goes across. And now that people are talking about things up to 112 gigabits per second, basically this is like radio frequencies that are outside the experience of most radio designers, going across a piece of copper trace on a circuit board as an analog signal, and you get it's amazing the kind of rat holes that you can get into. I mean, you discover things like different board manufacturers use different roughnesses of the copper underneath between the copper and the FR4 to get peel strength. And basically, the way that the electromagnetic wave at those frequencies travels, it's exquisitely dependent on the smoothness of the underside of the track. So you can double the the loss effectively by having a surface that's too rough. And so you have the people now, they use material with a you sacrifice peel strength. So these tracks, basically, they'll almost come off if you blow too hard, but basically they're better at getting the fast signals across. It's just endlessly fascinating and all analog, really.
I'd like to go back a little bit, if that's okay. Because you were at Burr Brown, you were doing, I mean, like, so we were talking about these big, broad topics here, but what were some of the implications of these, like on an everyday basis, right? So you said, well, I'm trying to help people figure out the solutions and stuff like that. It sounds like that means that there's a variety of methods to help people filter things. But what kind of chips did you end up designing or working on as a result of all this? That, I guess because as technology was progressing as well.
Well, I guess that the biggest job all the time that I was there, the time between joining Burr Brown and then Burr Brown being actually bought up by TI, it boiled down to an applications job, really, because people wanted to know how to get the best out of their system. And there were kind of several elements to that. One is that, a lot of the applications are quite low-end applications, and so they were serviced by quite low-end products. And one of the places where a mixed signal designer of a converter will often skimp is on the filtering. So, you need filtering both when you upsample to put stuff into a Delsig D2A converter, and downsample when you've finished converting analog with a modulator in an A to D. And that filter, can often take up a fair amount of space and power on the chip. And so people are always looking for ways to make that kind of smaller. And so they make a value judgment about how good the end performance of the product needs to be in order to make a decision, to priority call on how much space to allow that to take up. And sometimes the quality wasn't quite good enough for certain applications, and you would end up getting some high frequency stuff out that you didn't want. And so all of these things typically needed a bit of analog filtering afterwards. And so one of the things that I would do, because our designers, they understood a lot of things, but they didn't really know how to optimize the analog filtering back end. They did a good job designing the converters with their internal filters, cost optimized and therefore limited but very predictable in performance. But the filters that often got designed onto the reference boards, which were the ones often that customers used, maybe didn't do quite the trick. And so I brought, as soon as I joined, I brought some of that expertise, basically going, okay, if you use a slightly different topology, maybe add another RNSE here, connect it up like this, you can make something that has a notch there, which is going to notch out that thing that you don't want. And overall, make something which gave a better performance when people were interested in the kind of the high frequency rubbish that was coming out. So some of it was that. Some of it was just basically guiding people to do a better job of the analog circuitry they had to add. And some of it was related to the architecture of D2A converters that people were using. And to this day, it's still kind of a major issue. I suppose for most of my career, but certainly in terms of applications for, you were talking about at Burr Brown, the D2A converters, an audio D2A, produces an output which is equal to some digital fraction times a reference voltage, and overwhelmingly that reference voltage is still the power supply. So you need to have a really good power supply. I mean, a fantastically good power supply if you want good performance. And I think that kind of escaped a lot of people's attentions. So most of the problems that I've had, and I have them still. I mean, only a few years ago, I had to work with someone making a made for iPod accessory. It was a guitar interface. They had a weird distortion problem, which turned out to be a power supply issue.
And they're using the power supply instead of like a reference, like a voltage reference?
That's exactly it. That's basically, you have to get pretty much into kind of the audiophile range of things before the intrinsic power supply rejection of a D2A converter is actually independent, is actually good and independent of the local supplies. I mean, they're broadly wise to that kind of thing now, but still at the low end, you still find D2A architectures which actually just use the supply as a reference because they figure, well, gain stability isn't really important in that application. So if the supply voltage goes from 3.3 to 3.4, who cares? But it's what happens if the supply is going from 3.3 to 3.31 at a particular frequency. This kind of thing is clear as anything when you go looking for it, provided you know what you're looking for. So that's the kind of thing, in making an audio product much better in a way that the issue is discovered through measurement. But the people might say, well, it doesn't actually measure bad, but I want to know why it's doing that slightly weird thing. And having a suspicion that slightly weird thing, which doesn't necessarily look bad on the spec table, but you go, shouldn't be doing that. It turns out that it is something that can significantly affect the way that the product sounds. And I've had similar experiences with the different kinds of clocks that are used, for instance, in D2A converters, and different architectures are differently sensitive to the quality of the clock, the level of jitter, whether the jitter is white noise or whether it's structural jitter coming from some clock synthesis process. It's a real minefield. I've was solving those problems for people at Burr Brown and TI. When I went at TI, I focused more on the digital amplifier stuff, which was the kind of early days of digital class D, if you want to call it that. And even now with audio, most recently with the work that I was doing at Cypress, that the quality of the clocks that you had available was often the dominant driver of from the measurement performance, and also what the kind of, you might call them the golden ears people at various customers would think about the sound quality.
Yeah, it's interesting how much that does feed through over and over. And yet I still find myself like not checking the voltages. It's just like one of those things where it's like you just assume that the power is going to be fine. Oh, the light's on, it's great, but it's like, no. It's got to be a nice clean power supply. It's got to be a nice, well-apportioned clock and all these things like you're saying. And, for some reason, it should be the number one thing on a troubleshooting list, and yet it still seems to fall down a little bit. I don't know why.
Yes. I mean, gardeners have often said, a penny for the plant, a shilling for the whole. I mean, a shilling is an old unit of currency in England. It's a bit like saying, a penny for the plant, a nickel for the whole. I've certainly met hi-fi designers. There are some hi-fi designers who just want to use the best DAC available and use their own kind of creative smarts in pursuit of some imagined issue that they're going to fix, and therefore achieve the holy grail of fantastic sound quality. But there are others who realize that really you can get fantastic sound quality out of the most humble components if you actually do your design right. And so that's another one of the kind of schisms or splits in audio design. You can either go very complex or you can go very simple but carefully designed to actually be good at doing things that other people ignore. Power supplies is definitely one of those, and that's definitely a dividing factor, I think, in the quality stakes. Generally speaking, I mean, I can't claim to have listened to every amplifier on the market, of course, but the ones that seem to do better aren't the ones where some guy has some fantastic idea for a new topology, but where someone paid really, really close attention to the power supplies. Because if the power supplies are, a bad diet gives you an unhealthy person, really. And it's it's like that with electronics as well.
Yeah.
So, power is important.
Yeah. Well, and I think the other thing that I've, had hammered into me over my much shorter career is like that the circuit board is a component, right, in your design, and that the component and its drift is a component in your design, and the case and the heat and everything is a factor at the very least, if not a entirely beast of its own. And I think what I'm hearing is that, like, when you are paying that close attention, for example, with the power supply, you're integrating all these other things that seem like they just should work, these mental models of what these things are. You have to pay much closer attention because of, like you're saying, like you said, with the roughness of obviously that was much higher speed, but like the roughness on a SURDES connector, or the weave of a FR4, or whatever the small thing that might end up impacting your design. but you got to really pay close attention to it.
Exactly, that's exactly it. I mean, that takes me, more into the direction of stuff that I've been writing about more recently. But it's also the case that power integrity in general has become, a significant issue as people are doing more and more at high speeds and at high powers with switching power supplies and whatever. And I've kind of been trying to bang the drum for that for many years, really, because you're right in saying that the circuit board is a component, but it's not only physically a component because of what it's made of, but the layout itself is a component.
Yeah,
and
right.
Certainly in the case of audio, you could take the same circuit and give it to two different designers. They'll build two different amplifiers, and they sometimes will measure differently, and often people will say that they sound different. It's the same circuit, even if you use the same components. The build has an amazing effect. So greats in the kind of audio design field, like Doug Self. Don't know if you've done an interview with Doug Self.
We've not interviewed him. Dave actually knows him, and my co-host Dave knows him. So
yeah. So and he very early on was able to demonstrate that you would look at a typical push-pull amplifier, old school amplifier would need low value emitter resistors, and so the easiest way of making a small resistor that doesn't burn out readily is you get some resistance wire and you wind it into a kind of a coil. Yeah. It's got some inductance. That's not intentional, but you wind it into a coil and you stick it in. And he was able to show that that kind of thing is coupled enough to the distorted currents that flow in the two halves of a push-pull circuit that it's a source of distortion. It's a distortion that's very difficult to get rid of as well.
Right.
So just little things like that. The physical instantiation is not what you see on the schematic diagram. And so I've written a lot about the kind of myths of ground. People assume that ground or 0 volts or something. They have the one symbol for it. They assume it's a magical place where you can connect something to, and all your problems go away.
The current disappears into this ether, and then it just well, you don't have to worry about it anymore.
Kirchhoff be damned.
Right.
And especially when op-amp macro models that you get from manufacturers don't obey Kirchhoff's laws. That's the thing about Spice. I love Spice, and I've LT Spice, always have done, but it's not bound by physics. Its models they're not thermodynamically accurate usually. They in the sense that they can do things that the things in the real world can't do, for things like noise and energy, and also the models that you get from manufacturers, even sometimes from Linear Tech, although they were usually good.
I always think about the some of the sources, like the current source that's in there and stuff like that. It's like, oh look, I have 1 mega amp of current flowing through this thing now. I don't think that's actually right.
Yes, I mean, I make macro models where you just use them as kind of instantiations of math, and that's fine because it is a floating point system. You can have the most wacky versions of numbers if you're deliberately building that and you don't mind. But when you're actually doing a macro model, and so I showed, there's a 6-part piece of mine on EDN, because it was a kind of a reprint of that. On basically, I was determined to demonstrate that it made a difference what bypass capacitors you used on an op-amp circuit. Because there was always this kind of idea that bypass capacitors don't matter. You just need a capacitor and then the job's done. Or it's just there to stop the amplifier from going unstable for various reasons. But apart from that, it doesn't really matter. So, I worked through with simulations to show with actual simulations that it does actually make a difference. You can change the capacitor and it would change the output voltage. You're only talking about small effects, but when you're in audio, the small effects are the only things that you've got left.
Yeah, I've been tracking and learning more about RF lately. And if there's one lesson that I've been learning is nothing is as it seems with components. Every parasitic, everything really matters, and it seems like that could impact your.
Yes. I'll come on to that when you say parasitic, and I'll come on to that in a moment. But just to kind of wrap up on the amplifier side of things, an amplifier in a typical circuit, its output pin is delivering current into your load.
Right.
But where did that current come from? And there's plenty of macro models there out in the market where the current doesn't actually come from the power supply pins. So you're completely, you can't do any simulation of what's happening at the power supply pins because the op-amp is a magical source of current. It works as an op-amp, but the current that it produces comes out of a magical nowhere. And that's no good. You can't, and so, I would, work through very carefully to filter out these models, pardon the pun, that were not, if it doesn't, if it doesn't obey Kirchhoff's laws, then basically you can't take it seriously, because it's not really a model of what's going on if you're interested in whole level system simulation. And so you say parasitic, and Paul Rako is a great guy. I don't know if you've interviewed him. You probably have.
I know Paul. I actually haven't had him on the show yet, but yeah,
he's good. And and he wrote a piece. I usually basically just agree with everything that he wrote, but I had a slight kind of amber light on the one thing he wrote recently about adding capacitors to things. I think it was about snubber capacitors. He was quite right about what he was describing. But the thing is that when you start thinking about adding components, you lose the systems thinking side, because really what's important is the interaction between every component that you've got. An adding component changes your complete system. It's not incremental. So it's like chefs. Well, basically they'll kind of add something to the pot until they think it's right. One of my hobbies is mixology. I make cocktails, and I've got a friend up in Seattle who does the same thing. And his approach basically is he just has you have the mixing thing in front of him, loads of bottles on the desk, and he'll just be tipping things in and dripping things in and stirring around until he gets to something he likes. And he's designed some fantastic cocktails that way. But the downside is that it's very difficult to keep track of what you did, which means it's almost impossible to replicate it. So it is the one perfect cocktail. It's like, the joke that kills everyone, basically. It's kind of, there's only one of them. So you have to put a lot of effort in. So I'm much more of a kind of, okay, I get the measuring cups out and the droppers and things like that. I will put everything in to a known recipe. And if it's good, it's good. And if it's not, well, there's a little bit of like, okay, I can...
Right, you tweak instead of ripping it up. Right?
I can tweak, but I tweak with numbers. And so the thing about adding a capacitor, and that's one of the things I posted on LinkedIn when I started my burst of stuff earlier last year, was a presentation that I made at Cyprus, which is, just the rhetorical question, well, a capacitor can fix that, right? But the thing is that the system already should have comprehended the fact that some component was needed there. Just adding something is not once you've done the system design, is kind of, okay, what you're saying is the system design you had isn't right. So now you're going into empirical mode, and you've lost the credibility of any of the analysis that you did, because just adding a capacitor to something changes everything. So really what you need to have done is, in your system design, go, okay, well, there's going to be a capacitor there, and its value might be 0, but it might not be. So let's have it in the design and think, what are the consequences of doing that? So I'm not anymore the kind of person, maybe I suppose I used to be as a youngster in the sort of thrall of the ability to fault find. And you've probably done this. You've got a circuit on the bench, and the guy, the test engineer, is basically going, it's oscillating. And you come up to it and you put your finger on something and it stops. You put your finger on it, it stops. You go, okay, well, you need a 2.2 PAF capacitor there. Job done. You rub your hands together. You think, I'm so smart. That's why one day they'll pay me the big bucks. But, that might get you out of a hole that day. But if you don't realize why, then that's just, you can't build, credible electronics on that. You need to go away and go, why did that happen? What did I actually do? Did I put a pi of capacitors? I put some capacitors across that resistor, but actually I put some capacitors to ground on both of those nodes. And simulation is useful for that kind of thing, I must admit, as well as experimentation. I know the great Bob Pease, much lamented Bob Pease, was skeptical about SPICE and about how it could take you down the wrong direction. But, I do think it's like a calculator or a spreadsheet for engineers, basically, because if you're, up late at night at home without a breadboard in front of you and you want to know, well, what would happen if I put a capacitor there? It's, no substitute for building the circuit and going, okay, without capacitor, with capacitor. That's interesting. Do I understand that? And if you do, that's good. If you don't, you then have to, you do a hand analysis. I'm a great fan of hand analysis as well, even though now you can get programs like SAPWIN, SAPWIN, which is a symbolic analyzer, which basically, if you draw a circuit with component indices on it, and it'll give you the equation for the transfer function, which is really quite cool and saves you a lot of bother. But, I grew up without that kind of thing. So if in doubt, you draw the circuit.
Right, that's great.
And you jolly well do the analysis.
Yeah, in defense of Bob Pease, I remember reading, I've read a lot of his, what's all this SPICE anyways, and all his similar things. And I have a couple of his books. I think he always said he laments the fact that youngsters like me would go straight to SPICE. And then instead it was more like what you're talking about anyways, of, you have a model in your mind, you want to try something, and it's more convenient to switch it like that instead of going and soldering, desoldering, soldering, desoldering. I think that was the essence of what he was writing about a lot of the times.
In fairness, I think that's right. I mean, he has his, I know people who don't so much care for him. I think he was an important contributor to our art.
If nothing more than as a character, like
to read. Yes.
Him and Jim going within the same week was pretty tough.
That was that was terrible. Yeah, Spice is an important tool. You need to know how to use it. Spreadsheets, Excel is an important tool. You need how to use that. I use Excel a hell of a lot in engineering. Really,
you wrote about that, didn't you?
Scorecard thing. Basically, it's just a great way of seeing what's happening. I think it's an essential tool you need to understand. It really helps to be able to solve a problem several different ways. So if I'm designing a filter, I like to have several different ways in which I can look at issues that it might present. And sometimes, if you've got your coefficients in Excel, you can do things like, for instance, if you want to work out what's the maximum possible signal level out of something, basically, if an FIR filter, for instance, the trick is you take the absolute value of the coefficients and add them all up. So in an FIR filter, if you add all the coefficients together, that is the, if you like, the DC case, you get the DC gain. And if it's a filter that's designed to have unity gain at DC, you add all the coefficients together, the answer will be 1. But if you add all the absolute values of the coefficients together, you get an answer that's greater than 1, and that is the peak value that what I call the pessimal signal. That's the opposite of optimal. The pessimal signal will give you, and that's just if you take the impulse response of a filter. And just take the sign, the SIGN, the sign of that to make a little kind of chirp, a square wavy burst, if you like, and you put that into a filter, that will peak at the maximum value, which is the sum of the absolute values, and it's greater than unity. So if you happen to encounter a signal like that, and you're basically, what you did with your filter, you said, well, I don't need to worry about overload because it can never go greater than, look at the frequency response, it doesn't go above 1. But actually, you find out you could get up to 2, for instance. So you need to be very careful about understanding what the absolute worst case signal is you can put into a filter and design defensively around that. If you're not using floating point, I mean, people do floating point these days because it's so cheap, and basically the dynamic range is unbounded because you can have voltages up to 3 times 10 to the 308 volts, which is, but that's cheating. Really, if you want to do a real thing, and another thing. And I remember, actually, I went for a job interview, believe it or not that long ago. And one of the guys, questions they asked me was just simple stuff. It was the R and C I mentioned. Going right back to what you need to know about filters. You take an R and a C, and so he spun it around and said, what happens if you put a square wave into the capacitor, the CR circuit, into a capacitor resistor down to ground? And one of the things that people don't really grok until you've seen it happening on a scope is that if you put a 1 volt peak-to-peak square wave into an RC high pass, it's quite easy to get 2 volts peak-to-peak out of it. If you hadn't taken that into account in your design, basically, what it means is that your circuit, your system can overload on a signal you thought was safe. So you need to take that into account. And then the corollary of that is, for anyone out there who's ever used a state variable filter, that's the standard, what's called the KHN, Kerman, Huelsman, Newcomb state variable filter, 3 op amps. It has 3 outputs: a high pass, band pass, and a low pass. I used to use it a lot. It has some tremendous advantages if you don't mind spending a lot of op amps. But one of the problems is that if you're not looking at the high pass filter, if you're only taking the low pass output, what can happen is you put a square wave in, inappropriate square wave, the high pass output has this capability of doubling or in fact more than doubling. There's an expression for it, but you can get well more than 2 times if the circuit has actually if it's a complex pole pair. You're never looking at that, and so what happens is that the high pass output clips. And if the filter is clipping internally, it's not actually doing its job properly, but you can't see that because the output just still kind of looks all right. And that's something that I had to fix in someone's design that involved, some poor chap in Germany having to change 128 well, no, it would have been 384 resistors in a system.
Yeah, yeah.
Basically, we had to send him a lot of beer to do that, basically, because the customer was experiencing an unexpected and weird error, and it turned out that the signal they were putting in was clipping the high-pass filter, which wasn't actually part of the output. And so that's one of the other things I've written about, I think, possibly in one of my in electronic design pieces, is basically, when you're doing a simulation and it has got 10 op amps
Yeah,
in
definitely.
it, plot the
That's
outputs of all 10 op amps, not just the one you want, because if you don't look, you're probably not going to notice. You may assume that something's okay, but think about what the pessimal solution will be, and see what's going on. It's really important. Otherwise, this kind of unexamined, it's like the tree falling in the forest with no one seeing. Does it make a sound? And I can tell you that the op amp overloading in a circuit, no one can be looking, but it really does make the equivalent of a sound.
Right. Well, and I think at the end of the day, it's like you're standing outside the forest and you're looking to see if all the trees are falling down. If a crap ton of the ones in the middle are, you might actually care about that because they might just be falling the wrong way or something like that. You just don't know.
Yeah.
And that is one of the big benefits of Spice anyways, if you're simulating some larger system, you could see all the intermediates, you could see all the weird thing that might be happening. To make it akin to code, it's like you're seeing all of the problem states that you might not be exciting, but that are definitely there, and you just don't happen to see on the outside.
And that's a good way of putting it, because Spice, just like you can treat Excel as a programming tool. I mean, I don't program in VBA, but and I could do, and it's a great. It's a great tool, even if you can just express everything in formulae and just have a big mess of formulae there. But Spice, you can do the same thing. You can have behavioral sources which have quite complicated behavior, and I've used Spice quite regularly as a design tool. It's a kind of de novo. If I have no idea how something's actually even going to be built,
right.
I can do the work.
Yeah, it's very low risk.
There are a lot of people who'd say, use MATLAB or Simulink, Scilab, or something like that. But my personal tool has always been, well, I'll do it in Spice, because look, I can build a little behavioral thing which has my version of an FIR filter, but I can also put op amps on there. Basically, I can start building some stuff. I can prototype using that, and it's not quite the same thing as soldering components onto the board, but the advantage is I can put things in there that I don't have in my parts bin. I can make stuff up.
Well, and also you're not resoldering 348 resistors either, right? I mean, that's the downside to a hardware solution, is it's pretty fixed in meat space or atom space. It's like it's tough to redo.
And I can also find out what the performance of a million of them is going to be,
right?
With random variations. I remember once that I had to, for various reasons, I had to interview twice at Cyprus.
Oh, really?
In order to that's too long a story for this, but it wasn't a stand-up argument. It was because I was sitting. But basically, one of the guys who was there at the time, very, very smart guy, basically argued intensely against the need to have Spice simulation for something like the kind of embedded micros we have. Basically, he said, because it's so easy just to build what you want on the desk and look at it in front of you.
Oh.
And I am not at one with that approach, because for a start, you may not you may not know what you're looking for if you're a novice. So you can build it, but if all you do in your engineering life is build something and then basically do a combination of hacking the code and crossing your fingers until it works, that's not engineering. And also, you don't really know what's going to happen if you build a million of them, because 1,000 of them might not work, and you can't get an indication of that by sitting at your bench. So I don't mind.
By the time you figure that out, it's much too late. You've already built a million.
Exactly. So I don't know how you could really design something without the ability to validate it very thoroughly, and it doesn't have to take a lot of time. I think if you don't simulate because you don't think you know how, then you probably don't understand your circuit well enough. You should be able to express it in some form which is amenable to having it crunched on a computer in some way. Otherwise, kind of, you're more just a kind of gifted amateur.
Mm-hmm. Yeah.
Really, that kind of dilettante approach, and I speak from experience, because I'm sure that I was more like that when I was young, in the days before computers and stuff like that. As I said, I was quite ready, fire, aim, and was lucky to do something. But over time, I realized that that's not the way to do it.
Right. I think Adam Savage or someone says the difference between science and messing around is writing it down. And, if you add rigor and all the other experimental method in there too, I think that kind of gets towards it, right? having some process and having some rigor really is what makes engineering a thing.
I know, and it's kind of, basically, if you do something, that something has to align with your expectations, because there's always two things that could be wrong. Either the thing you're doing is wrong or your expectations are wrong.
Yeah, right.
The only time it really works is when you have an expectation, you do something, and it actually it aligns with it. Because if it doesn't align with it, it's like, I'm from a philosophical point of view, great believer in Karl Popper. It basically, when that effectively falsification or disproof is the only thing, because you can do many things that agree with what you're doing, but the first thing you do that disagrees with what you're doing, that difference is the important thing. Basically, you can disprove something in that way, in a way that you can't prove it. So, and I think that kind of thing is it's lost to a lot of quasi scientific thinking that is kind of going around the world on a lot of subjects at the moment. Experimentation is important, and you need, if you do the experiment and you're completely happy with that you did it right, and that's the result, and it doesn't correspond to your theory, then your theory is wrong.
That's right. Yeah.
Yeah. End of story.
Right.
And I think that you have to. That's why you have to be prepared to be wrong. You absolutely need to be prepared to be wrong. You can't go through your engineering life hoping that everything you do matches, because that's, you're not doing anything new. One of the things my dad used to say to me is, the man who's never made a mistake has never made anything.
Yeah, that's a great phrase. Yeah. And
I was reading Eric Bogotin's 20 sort of rules for engineers or something was linked to in LinkedIn, and one of them is basically an expert is someone who's made all the mistakes or something like that.
Yeah, right. Seen everything,
and it's true. So I remember one of my I was a industrial supervisor for someone's PhD program while they were working for me back in the chemo days, and we got into a disagreement about something, and I was pretty sure something went a certain way, and he was sure it went a different way, and so he thought about it again, and eventually, it turned out he'd made some mistake, in his hand analysis, and what actually came out was what my intuition said, and he said, "Well, thank goodness for that, because I couldn't imagine that you were wrong." And I thought that was that, and I was kind of a little bit concerned about that, really, because you don't want people to assume that you swing by their desk and you say something and it's always right, because that stops people from being creative and thinking about things for themselves. Again, if we can't solve this problem, we'll get Kendall in and he'll fix it, and then we'll move on. That's kind of I've over the years kind of tried to get out of that situation, because I love mentoring people, but the whole point is to give them the tools they need to solve their own problem, not just to give them a channel to ask me how to solve it. That's what often happens on the web. Basically, as soon as I link with someone and he says, "I've got this problem, can you solve it?" As if I was a kind of homework machine. So I really, I spend a lot of my time at the moment kind of guiding people to kind of thinking of things a little bit more clearly, maybe getting the right kind of books or looking at the right things. But it's kind of just solving someone's circuit problems for them it's not going to help anyone.
Well, I think in the age of Google too, it's kind of the expectation. Google, Stack Exchange, all those things. It's like, well, I just need this thing, then I'll be done. So, well, yeah, but then what if it doesn't work? You're kind of screwed. So, yeah. I wanted to briefly touch on like there's a lot of types of filters out there, and I'm sure that that's one thing you guide people towards is just like topologies and similar things. How do you go about guiding people towards what feels like a wide field of ways to filter, but like differentiating between the Chevy Chevs and everything that's out there? I guess
it's a sort of like what I imagine, because I haven't experienced, is the personal shopper experience. If you want to get some help in a fancy department store or something like that, and so you'll have a little interview with this person who's going to help you find the right shirt or tie or perfume or whatever like that, and they'll ask you questions, in order to narrow in on your kind of personality type and all that kind of thing. And it's the same, I think, when people ask that general question, is you have to start digging into what it is, where are their kind of priorities, where are the boundaries. I mean, there's always kind of rudimentary spider diagram that you can pull out on, power consumption, solution size, cost, what's the signal, what's your expectation, I have genuinely had people who say, well, yeah, I want to filter. I want to filter the signal, but I don't want it to change the signal shape. And I'm going, well, that's impossible, because basically the signal that you've got contains some stuff that in your mind you think is the right stuff, and some stuff that in your mind you think is the wrong stuff. And now your ideal filter is the thing that's going to take the wrong stuff away, but inherently it's going to change the shape, because if you take the wrong stuff away from the signal, it isn't going to be the same shape anymore. So whatever you do, if the filter is having any effect, it's changing the shape of the signal. So let's refine that. What do you actually mean you don't want to happen to the signal? And then you get into lots of things about, well, I don't want there to be any overshoot, even though they're maybe not putting any kind of a signal in that's going to provoke an overshoot. Or they'll say, well, I absolutely have to have linear phase, because then I'm not going to get any waveform distortion. But then, they choose something which has got a roll-off in frequency response, so you take away some of the harmonics and it changes the shape of the signal. So really, the process of solving the right filter for people, first of all, is basically digging in. What do they think is going to happen when they filter the signal? What for them, what does success look like? They're going to filter the signal, and then they're going to do something else to it, and they've got another black box in there further down the chain that does something else with the signal, and maybe it tells them something useful, like power, or the kind of second moment of some impulse, or there's something ultimately they're going to need to know. But typically, when people ask about filters, I often find that they haven't thought that bit through enough yet. So they don't really know what they want. It's not usually a case that all they really need is say an anti-aliasing filter. And sometimes when it is an anti-aliasing filter, I mean, for instance, I've had people who will say to me, they don't want to use the kind of a sharp brick wall, to use the old-fashioned term, brick wall filter, because it's going to make the impulse response have more overshoots. And I'll point out that their system already has a brick wall filter in it. So adding another brick wall filter is completely invisible. It's not going to do anything at all to the impulse response. Because, two brick wall filters, together, provided they're kind of linear phase and fairly sharp, it basically just looks like another brick wall filter. Or, they'll say, well, I've got the system bandwidth is limited to 20 kilohertz by some sharp filter, and they're worried about the impact of a 250 kilohertz RC pole. They say, well, is that going to have some effect? And I go, well, no, it's not going to have any effect. Now, it might do something useful in your system, but what is it that you actually wanted to do? And actually persuading people to think about what they want to do often almost it defines what they need, and then if they and that often gets them there. In terms of the detail, I mean, people say, you know a lot about active filters. Which topology should I use? Should I use multiple feedback, or should I use cell in the key, or Norbert Flieger's lovely GIC based thing, which is a great filter, or the 3 op-amp per state variable, or maybe I need to do something that's based on the very good properties of a doubly terminated ladder, and so I could use FDNRs, or I could use Leapfrog, but I often, those are people who are just kind of, they're reeling off the stuff they read,
Right. Yeah.
It's kind
There's
of
like a laundry list of,
it's a laundry list.
They have like a list, a checklist. Yeah.
You have to, if you're commercially in a business of making stuff, you have to make money. You don't want to spend more money than you have to. Someone said that an engineer is someone who can do for 10 cents what only damn fool could do for $1. You can, typically people don't want to spend much money. So it's okay. Well, here's a single op-amp thing. And I don't want to have any accurate components. I don't want to have any close tolerance components. So I say, okay, I don't want to pay. Yeah, you can have components that aren't close tolerance, but then if you make 1 million of these things, they're not all going to be the same. Is that all right? And then you can go down. You say, okay, well, they're going to be all over the place up here at this frequency range, but that's not important. They're going to be very closely matched down here. Guess what? Simulation is a great way of doing that with Monte Carlo analysis. So sometimes you have to get past people's kind of they've already decided something they don't want, but they haven't really thought it through. So, it is just an organic process, really. And at the end, you come up with, something hopefully which meets their goals. I mean, I did have one customer who was adamant that they wanted, he said, I've only got room and I've only got space and the power for one op-amp. So can you solve this problem, which wasn't it wasn't a filter so much, although it was a transimpedance amplifier with a varying input capacitance load, because it was monitoring a photodiode that was rattling backwards and forwards inside a disk drive. But eventually, because it happened, this was at Burr Brown, we happened to have a nice, fast decompensated dual amplifier in a small package, each of whose amplifiers were very low current, that I could meet the budget that he imagined he could only meet with a single op amp with 2 op amps, and therefore design a much better circuit. And what I was then able to do was do an analysis of his system and build something which is do a filter analysis such that I could position the input capacitance as a variable and adjust the transfer function so that as that capacitance varied, it had like a parabolic error curve rather than a linear error curve. So the transfer function of the whole transimpedance amplifier varied a lot less, because the thing was designed as a filter where you needed to have one parameter, which is one of the input capacitors, was variable. But I couldn't have done it with a single amplifier. I needed to have this 2 amplifier design, but I had to break the customer's specification that he only wanted to have a single amplifier, because what he really meant was he only wanted to have a single package. And also because the amplifiers were low power amplifiers, I still met his power consumption requirements. So sometimes you hear what the customer says and you have to go, well, okay, I will infer from that what you need, and I'll design something that fits what you need.
Well, speaking of hearing things, I think we have to definitely call out probably the only time this will ever happen. The microphone that you were speaking into right now, you helped design one of the chips that at least was formerly designed into the microphone that we ship to people.
It's quite possible.
That's
yes, the particular
crazy.
manufacturer of this that I'm talking to, I can't say for certain whether now, several years on, they're still using it or whether they've moved to something cheaper or whatever. But this particular manufacturer, there was a time when Cypress was very active in the USB audio space, particularly for Apple accessories. As was the case, we always had to try and make our part, the PSOC, great part. In all its variants, do something that people wanted to do, and so I designed effectively the clock recovery system for early generations of what's called the synchronous mode of USB audio, and that's a mode where the peripheral needs to be able to create its own local audio clock effectively from timing information it receives from the host, the USB host, PC or whatever. And the only information you ever get from the host in a sort of full speed USB is the 1 kilohertz, the 1 millisecond packets. So basically what you have to do is you have to create something like a 22.5792 megahertz clock, and the only thing you've got is 1 kilohertz. So people might say, well, why don't you multiply it up on a PLL? But the answer is you get rubbish, because that's way too much to multiply it. So
starting too slow, right?
So starting with the bits and pieces that we had available, I designed a system which enabled the thing to exactly create identically create the required clocks. On the assumption that at the other end, the 22.5792 megahertz clock would have been created the same way, i.e. the PC only had one timing system. So that was what the downside of that is, of course, you're generating a local clock, and we were doing it with a chip which wasn't really designed to do that. So it had its shortcomings if you were doing ultra audiophile stuff, a little bit too much jitter for some people's tastes.
Right, but I was going to say we don't really ship ultra audiophile mics to our guests, unfortunately.
No, it would be
maybe someday.
It would be fine for this. I mean, what they do, what is now used is the asynchronous mode. It suits people much better, because now you use the smarts that are available in better USB hosts and better drivers and things like that, where the peripheral can say to the host, "Oh, hang on, slow down or speed up a bit." And so you occasionally get a packet with one too few or one less or one extra word in it, basically. And so you throttle the link, so you can have your own local clock that's as high quality as you like. So the audiophiles guys like that, so they can spend hundreds of dollars on a super low phase noise clock for their D2A converter, and basically the USB interface basically monitors the some pointer, sort of lagging leading thing, and will occasionally tell the host to speed up or slow down. incrementally, and that, you know, so that's a much higher quality. And it turned out that you know, we could do that solution with our chip, but by the time we implemented that on a subsequent chip, you know, the market was already moving away from wired connections to wireless. So, you know, in a way, I'm surprised that this microphone isn't already a Wi-Fi microphone. I'm sure that there are options for that where you don't even have to have any wires at all.
I don't trust wireless.
No, me neither.
I still, yeah. Nothing like a bit of copper.
But there we are. Yes, so that's the, you know, maybe there is still a little bit of me in this in the microphone in some way. So, you know, this thing about, you know, transducing, tracing the signal. You know, at some point the signal gets chopped up into little pieces using a piece of circuitry that I designed.
That's super cool. Well, Kendall, where can people find more of your articles and more about you and what you've been working on as the filter wizard?
Well, if you want the fire hose approach, you can just Google my name. If you want to see some of the stuff that I've been sort of just basically fire hosing onto LinkedIn, you can go to my profile on LinkedIn, and LinkedIn supports hashtags, something that a lot of people don't know. So if you just search for the hashtag filter wizard, so hash filter wizard, all one word, you because I try and remember to put that in all the pieces I put on LinkedIn, you'll find that there. There's the stuff on Planet Analog. It's a growing list. So you just go there, search for my name, you'll find my author page. Likewise, EDN. Electronic design have also gone through a bit of a kind of thing. You can find my pieces on electronic design, but there isn't an author page with an index right at the moment. Yeah, but if you search maybe for the Chronicles of Ground, as in GND, Chronicles of GND, you'll find the kind of stuff, my musings on ground. Yeah, and so there's all sorts of stuff out there, spread all over the place, not in one place. So, you know, you have to go searching for it.
Well, Kendall, thank you for being on the show, sharing your broad knowledge about audio and filtering, and just it's been great.
I look forward to hearing it with all the kind of long-winded, boring stuff chopped out.
No, this has been great. Well, thank you for being on the show. We'll talk to you soon.
Yeah, take care.